I hope that we established that a function f of x equal to x raised to the power of n, where n is some discrete number like 1, 2, 3, 1, 2, 3, 1, 3, 1, 2, 4, 1, 4, 1, 2, etc., can be represented by the volume of an n-dimensional object which extends from the origin to the x position along each dimension, and all of its sides are of equal x size. The situation gets a little complicated when we try to increase the volume of this object by making each dimension larger by a slight amount delta x. When this takes place, we have to consider what are all of the small volumes created that represent delta f of x. In case of n equal to 1, we have a one-dimensional line the length of x representing f of x. When we add another delta x to this amount, there won't be any other one-dimensional volumes other than the old x volume and this delta x volume which we just added. It doesn't make sense to talk about x times delta x volume, since this would create an object with more dimensions than f of x has. In case of n equal to 2, simplicity gives way to complexity. We know that we need to have various combinations of components from side 1 and side 2, which are composed of x and delta x, and when combined they will create the whole that we will call delta f of x. The x and delta x, which belong to side 1, will be written like this: x1 and delta x1, while the side 2 components will be written like this: x2 and delta x2. If we take a look at the combination x1 and x2, it is immediately recognized that this isn't a part of delta f of x, since this piece is the actual f of x itself. We may also conclude that any n-dimensional combination of sides that composes a volume which is entirely composed of x values is the actual function and not a part of the change in the function. Next, we examine the two sides, x2 and delta x2, and we recognize that they actually form a line and not a two-dimensional volume which is a part of delta f of x. This immediately disqualifies the combination x1 and delta x1 as well, and leads us to a rule that says that any volume composed of the same side and its change in the side doesn't have the sufficient number of dimensions to matter in the n-dimensional delta f of x. After this failed attempt, we try x2 and delta x1, and we are finally met with success. This combination of sides, as well as x1 and delta x2, happen to create volumes which are a part of delta f of x. Notice that the combination of sides x1 and delta x2 can be written as delta x2 and x1, but it will describe the same volume. The last possibility to create a volume is a combination of delta x1 and delta x2. And indeed, we find that this volume does show up in our graph. If we cared to do this in a more formal way, we could say something like this. In the case of n equal to 2, we know that there are three volume types that can exist. One volume type where both of the sides of the volume are composed of x components. The second volume type will have one side composed of an x component and the other will be composed of a delta x component. The final volume type will be composed of sides which are only delta x components. Looking at the first type of volume, we know that we have two x sides to choose from in order to create the two-sided volume. In the two-dimensional case, it is obvious that this leaves us with only one possibility. The formal process by which we come to this conclusion is as follows. There are two possible sides to choose from to be our first side of the volume. Once we choose our first side, we are left with only one other side to choose from in order to compose our two-dimensional object. This means that we have 2 times 1 possible volumes. But something must be wrong here. How can there be 2 possible volumes when we know that there is only one? The reason behind this is that our procedure doesn't stop us from choosing x1 and x2, but then choosing x2 and x1 the next time. In order to eliminate duplicate ways of enumerating the sides of the same volume, we must ask ourselves how many duplicate ways are there to state all of the sides of a two-dimensional object and then divide our result by that number. In this example, we know that there are 2 ways to write down the sides of a two-dimensional object, but there is a more formal and general way of saying this. We know that we have 2 sides to work with. If the order in which the sides are written down does matter, then we can simply say that for the first side we can choose from 2 choices, x1 or x2, and for the second side we have only one choice, whatever is left, x1 or x2. And for that reason, there are 2 times 1, which is 2 different ways to write down the sides of a two-sided volume. Dividing possible volumes that we have enumerated by the number of different ways that a two-dimensional volume can be enumerated, we get 2 divided by 2, which is 1. We just discovered that there is only one two-dimensional object composed of x sides. This may still be somewhat confusing, but the next volume type will get us closer to understanding the situation. The second volume type is composed of one x side and one delta x side. It should be noted that the volume must have the same number of dimensions as the object representing f of x. Furthermore, there can't be duplicate uses of the same dimension in the description of the volume or the use of x and delta x of the same dimension in the description of the volume. These properties force us to conclude that if a volume isn't composed of the x side of a particular dimension, then delta x side of that dimension must be used. Going further with this line of reasoning leads us to conclude that each dimension must be listed, and once x components of the volume are picked, then the delta x components of other dimensions are also determined. For this reason, a volume is unlike any other if its number and selection of x sides is unique. In this case, one side is composed of an x side, while the other one is composed of a delta x side. There is a choice of 2 different x sides to choose from for the first and only x side, so we can simply say that there are 2 possibilities. Since we only listed a single side, there are no duplicate ways of writing it. For this reason, when we look at the number of volumes that we can enumerate with one x side and divide it by the number of ways that we can state the same volume in our enumeration, we get 2 divided by 1, which is 2. Simply put, there are 2 volumes with one side of x and the other side of delta x. The third volume type is composed of only delta x sides, which is a very similar case to the one where the volume was composed of only x sides, and for similar reasons we could only conclude that there is only one such volume. The entire two-dimensional case can be summarized down to f of x plus delta f of x is equal to x times x plus 2 times delta x times x plus delta x times delta x. And now it's time for fun in 3D. In the case where n is equal to 3, we know that there are 4 types of volumes. By now, it should be apparent that there are always n plus 1 types of volumes, where one type of volume represents f of x, and the other n types represent the change in the f of x. The first type has all x-length sides of different dimensions. We have 3 dimensions to choose from, x1, x2, and x3, for the first listed dimension. Then we have 2 unique dimensions to choose from after that. For example, x2 or x3 if x1 is already chosen. Until we finally are left with only one dimension, x3 if x1 and x2 are already chosen. This leaves us with 3 times 2 times 1 listed volumes, but the volumes are the same regardless of the listed order of their sides. One volume has 3 sides. There are 3 possible sides that can be listed first, then 2 unique sides that can be listed next, and finally, one side that is left to list. This leaves us with 3 times 2 times 1 ways to list our sides. We divide 3 times 2 times 1 listed volumes by 3 times 2 times 1 ways that a single volume can be duplicated in a list, and we are left with one volume composed of only x sides of different dimensions. By now, this volume should be recognizable as f of x. The next type of volume is the one with 2 x-length sides of different dimensions and one delta x-length side of a unique dimension. In order to figure out how many such volumes there are, we must consider only how many surfaces with 2 unique x-length sides of different dimensions exist. Once the x surfaces are chosen, then the delta x sides automatically follow. To do this, we must recognize that there are 3 different dimensions of x-length sides to choose from first. Once chosen, there are only 2 other choices of x-length sides left for the surface. This means that there are 3 times 2 different x-length surfaces that are enumerated. We mustn't forget that we have enumerated surfaces more than once. There are 2 listed x-length dimensions in each surface, and this means that for the choice of the first dimension to be listed, there are 2 options to choose from, while there is only one other option left to be listed as a second side. This means that there are 2 times 1 ways to denote a single surface. Combining the two effects leads us to conclude that 3 times 2 enumerated surfaces divided by 2 times 1 ways to duplicate surface enumeration gets us 3 truly unique enumerated surfaces. The type of volume that follows only has one x-length side of a unique dimension and 2 different delta x length sides of unique dimensions. Following the same line of thinking as before, we can choose one of the 3 unique x-length dimensions for the first dimension. Since there is only one dimension listed, there is no way to double its enumeration, and we are left to conclude that there is 3 unique volumes with a single unique x-length dimension. Finally, we are left with the last volume type, which involves only the delta x length sides of unique dimensions. We can explain the fact that there is only one in existence in the same fashion as we did for volumes of x-length sides of unique dimensions. Alternatively, we can say that since there are no x-length sides present, then all of the delta x sides are chosen by default, and therefore no variations of this type can exist. Now this all boils down to f of x plus delta f of x being equal to x times x times x plus 3 times x times x times delta x plus 3 times x times delta x times delta x plus delta x times delta x times delta x. In 4 dimensions, where n is equal to 4, this property looks like this. F of x plus delta f of x is equal to 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times x times x times x times x plus 4 times 3 times 2 times 1 over 3 times 2 times 1 times x times x times x times delta x plus 4 times 3 over 2 times 1 times x times delta x times delta x plus 4 over 1 times x times delta x times delta x times delta x plus 0 factorial over 0 factorial times delta x times delta x times delta x times delta x, which comes out to f of x plus delta f of x being equal to x raised to the power of 4 plus 4 times x cubed times delta x plus 6 times x squared times delta x squared plus 4 times delta x cubed plus delta x raised to the power of 4. So then, the delta f of x is equal to 4 times x cubed times delta x plus 6 times x squared times delta x squared plus 4 times x times delta x cubed plus delta x raised to the power of 4. In 5 dimensions where n is equal to 5, the formula is f of x plus delta f of x is equal to x raised to the power of 5 plus 5 times x raised to the power of 4 times delta x plus 10 times x cubed times delta x squared plus 10 times x squared times delta x cubed plus 5 times x times delta x raised to the power of 4 plus delta x raised to the power of 5. Delta f of x is then equal to 5 times x raised to the power of 4 times delta x plus 10 times x cubed times delta x squared plus 10 times x squared times delta x cubed plus 5 times x times delta x raised to the power of 4 plus delta x raised to the power of 5. You should be noticing by now that the first term in delta x is always a multiple of n. We formally know that there will always be n times n minus 1 times n minus 2 times n minus 3 and so on down until we reach 4 times 3 times 2 times 1 enumerated volumes and n minus 1 times n minus 2 times n minus 3 and so on down till we reach 4 times 3 times 2 times 1 ways to give duplicate names of those volumes, which results in n unique volumes. This is another way of saying that there are only n surfaces with unique x-length dimensions on their original f of x volume. These will be the only surfaces composed entirely of x-length dimensions, which will expand by delta x to compose a part of a greater delta f of x volume. In any case, only the first term, which is multiplied by n, is left without its delta x when we divide both sides of the equation in order to find the rate of change delta f of x over delta x. This becomes important because in order to find the derivative, we must make the delta x infinitesimally small, and that makes all the other terms too small too quickly to stay relevant. This means that the derivative is defined by the first term of the sum describing delta f of x. If the number n is chosen to be an integer and a positive one, like 1, 2, 3, 5, 8, 2, 9, 1, 2, 3, 4, 1, 2, etc., this term will always be n times x raised to the power of n minus 1. You had to ask for the details, so there they are.